Welcome back to DeFi Exploits Explained. Today, tx.origin phishing, a classic authorization bug where a contract trusts the wrong who, in three clear acts. First, the honest flow, the owner spending their own wallet, then the attack, where the owner is tricked into clicking one malicious contract and it empties the wallet without ever stealing a key or a signature, and then the one-word fix. And we prove each act on a diagram and in a test where you watch every balance change. Let's go. First, the key idea, and it's one distinction. When a transaction runs, there are two different notions of who is calling. Text origin is the human account that started the whole transaction, the person who signed it. msg.sender is whoever made the current call, the immediate caller. If you call a wallet directly, those two are the same, you. But if you call some other contract and it calls the wallet, then from the wallet's point of view, msg.sender is that middle contract, while tx.origin is still you, the human, at the very start. So if a wallet authorizes spending by checking tx.origin, then any contract the owner is tricked into calling can spend the wallet, because tx.origin is still the owner the whole way down. Let's see honest first. We build it in Foundry. Here is the skeleton of the wallet. It remembers its owner set once in the constructor, and it has a transfer to function to send ETH out. The guard inside transfer to is the whole story, so let's fill it in. Here is transfer to, and here is the bug on one line. Require text.origin equals owner. The intent is only the owner may spend, and it looks right if you call this directly. text.origin is you, the owner, and it passes. But text.origin is the human who started the transaction, no matter how many contracts sit in between. So it doesn't actually check that the caller is the owner. It checks that the owner is somewhere back at the start of the call chain. That's the whole. First, let's use the wallet honestly, and it behaves perfectly. Act 1. The honest flow on the diagram. The owner calls the wallet directly, transfer to, send 3 ETH to a friend. Because the call is direct, both who's are the owner. tx.origin is the owner and msg.sender is the owner. The guard, tx.origin equals owner, passes, and the wallet sends the 3 ETH exactly as intended. Called directly, tx.origin and msg.sender are the same person, so nothing looks wrong and nothing is yet. Now let's prove it. Here's the honest test. The owner funds a wallet with 10 ETH, then calls a transfer to directly to send 3 to a friend. Both tx.origin and msg.sender are the owner, so it should just work. Watch the numbers. Run it. The owner sends 3 ETH to a friend. The wallet goes from 10 to 7 and the friend receives 3. A direct call by the owner, working exactly as intended. That's the honest flow. Now watch what a middle contract does to it. Act 2, the attack on the diagram, and it all happens in one transaction the owner starts. The attacker publishes an innocent-looking contract, say a claim your airdrop button, and gets the owner to call it. Step 1, the owner calls the attack contract, claim airdrop. At this point, text.origin is the owner, and so is msg.sender, because the owner called it directly. Step 2, the attack contract turns around and calls the wallet, transfer to, send everything to the attacker. Now, from the wallet's view, msg.sender is the attack contract, but tx.origin, the human who started it all, is still the owner. The guard checks tx.origin equals owner, sees the owner, and passes. So the wallet drains its entire balance to the attacker. The owner never signed the transfer, never leaked a key, they just clicked one button. Let's prove it. Here is the attack test. The owner has a wallet with 10 ETH. The attacker deploys the phishing contract pointed at that wallet. Then the owner tricked calls the attack contract, and we set both msg.sender and tx.origin to the owner because the owner really did start this transaction. We print the before and after. Run it. Before, the wallet holds 10 ETH, the attacker holds nothing. The owner clicks the phishing contract once. After, the wallet is at 0 and the attacker holds all 10. One click and the whole wallet is gone, because the guard trusted text.origin, the human at the start, instead of msg.sender, the contract that actually made the call. Now let's follow that ETH on a real blockchain. And here it is live, on a real chain, every command reproducible. we deploy the vulnerable wallet and fund it with 0.02 ETF, then deploy the phishing contract pointed at it. Before we read the balances straight off the chain, the wallet holds 0.02, the attacker holds nothing, then the owner, the tx.origin, sends one single transaction, click the phishing contract's claim airdrop. After, the wallet is at 0, drained, and the attacker holds the full 0.02 stolen, and to see exactly where the ETH moved, we replay the transaction's internal call trace. Look at the nesting. Claim airdrop calls the wallets transfer2, and transfer2 sends 2 times 10 to the 16th double way, 0.02 ETH, straight to the attacker. One click by the owner and the contract they merely called walked the whole wallet out. Now let's fix it. Act 3. The fix on the diagram, and it is genuinely one word. Change the guard from tx.origin to msg.sender. Require msg.sender equals owner. msg.sender is always the immediate caller, the contract or account that made this exact call, and the middle contract cannot fake it. Now replay the identical phish. The owner clicks the attack contract calls the wallet, but this time the wallet asks, is my caller the owner? And the caller is the attack contract, not the owner, so it reverts, not owner. The phish fails. And the normal direct call by the owner still works, because then msg.sender really is the owner. Authenticate the caller, never the origin. Let's build it and prove it. Here's the fix in code, and it's the single word we've been building to. The guard becomes require msg.sender equals owner, that's it. msg.sender is whoever called this function directly, so a phishing contract in the middle now shows up as the caller and gets rejected. The rule for every access check you ever write: authenticate msg.sender, the immediate caller, never tx.origin. The tx.origin has almost no safe use, and this is exactly why. Here's the fixed test. Same setup, a wallet with 10 ETH, the same phishing contract, the owner tricked into clicking it in the exact same way. The only thing that changed is the wallet's guard, now msg.sender instead of tx.origin. We expect the whole thing to revert. Run it, then the owner clicks the identical phishing contract, running the identical move. But now the wallet checks msg.sender, sees the attack contract, not the owner, and reverts with not owner. The phish gets nothing, and the wallet keeps its full 10 ETH. Same attacker, same click, and the attack is dead because we authenticated the caller instead of the origin. One word. Quick recap. There are two who's in a transaction: tx.origin, the human who started it, and msg.sender, the immediate caller. If a wallet authorizes spending by checking tx.origin, then any contract the owner is tricked into calling can spend the wallet, because tx.origin stays the owner all the way down the call chain. That's the phish. The owner clicks one malicious contract, it calls the wallet, and the wallet drains. No stolen key, no signed transfer. The fix is one word: check msg.sender, the immediate caller, which a middle contract can't fake. Authenticate the caller, never the origin. A quick note, rebuilding these hacks safely and explaining them line by line takes real work. If it helps you, the wallets are on screen and there's a Ko-fi link below. Every tip funds the next breakdown. Thank you. And that's tx.origin phishing, told in full: an honest owner spending their own wallet, a single click that drains it through a middle contract, and the one-word fix that stops it, each act on a diagram and in a test. Next episode, another DeFi exploit rebuilt from scratch and then fixed. Subscribe so you don't miss it, tell me in the comments which exploit to break down next, and I'll see you there.